Picture this. There's an industrial process where almost 80% of the material just vanishes, but what's left becomes exponentially more valuable. How can wood lose nearly all its mass and transform into a global energy resource that countries pay billions of dollars for? Every year, this product makes a journey from living forests to cargo that crosses oceans, fueling everything from backyard barbecues to high-tech industries. But behind the apparent simplicity lies a dangerous stage where one mistake can destroy dozens of tons in minutes. In this video, you'll see how fire is controlled without flames. And by the end, you'll learn a fact about charcoal that'll completely change how you think about its true cost. Every year, the world burns through roughly 73 million tons of charcoal. That's nearly 200,000 tons a day, enough to bury hundreds of stadiums under a thick blanket of carbon. Despite the rise of gas and electricity, the global charcoal market is worth $3 billion annually. It all starts at raw material yards, where millions of tons of freshly cut logs arrive every single day. First stop, automated sawing lines. The wood gets chopped into standardized lengths, then moves on to hydraulic splitters. Massive steel blades, under incredible pressure, crack the logs into smaller pieces with uniform cross-sections. This isn't for looks. If the logs are too big, the outer shell carbonizes completely while the core stays raw. If the pieces are too small, they'll burn up too fast, turning into brittle charcoal that crumbles into powder. Uniformity of size. That's the foundation of quality, laid down before the first spark ever appears. Freshly cut wood contains 40 to 60% moisture by weight. Evaporating that much water directly in the kilns would be wildly inefficient, so the wood heads into sealed drying chambers. Each batch processes roughly 28 tons of wood over 12 hours. Powerful fans and circulation systems push hot air evenly through the stacks, dropping moisture levels to the critical minimum needed for safe transition to the carbonization stage. After drying, the wood gets loaded into giant industrial kilns. One kiln can hold around 55 tons of wood. This is the most critical stage. The kiln entrance is sealed tight with brick and a thick layer of special clay mixed with sand. This creates a low oxygen environment where combustion doesn't happen. Instead, you get pyrolysis, the chemical breakdown of wood through heat. The process runs non-stop for 7 to 10 days. When the internal temperature hits 572 degrees Fahrenheit, thick white smoke starts pouring from the vents. That's the operator's signal that transformation has begun. Operators, or automated systems, precisely control the air supply. There needs to be just enough oxygen to sustain the reaction, but not enough to let the wood burst into open flame. The result of this process? 55 tons of wood becomes just 11 to 13 tons of finished charcoal. Almost 80% of the original mass is lost, but what remains is pure carbon, lighter, more energy dense, and a cleaner burning fuel. When pyrolysis is complete, the charcoal still holds extremely high internal temperatures. Even the slightest contact with oxygen at this stage can trigger spontaneous combustion. To prevent disaster, the charcoal is left to cool in sealed conditions for 10 to 14 days. It's a test of patience. One tiny crack in the seal, and dozens of tons of product turn to ash in minutes. After full cooling, the charcoal goes through mechanical sorting. Large intact chunks 5 inches long are considered premium product. Every year, just one large plant's automated packaging lines process about 22,000 metric tons of this charcoal, which then gets shipped all across Europe. But what about the small fragments and charcoal dust? At a modern facility, nothing goes to waste. All the charcoal scraps get ground into powder and mixed with natural binding agents, like cassava or cornstarch. The resulting mixture is compressed under high pressure into briquettes, cylinders, or perfectly uniform pillows. These briquettes go through final drying at 280 degrees for 2 hours, becoming dense and stable fuel. When you look at the logistics side of a large modern plant, the numbers get even more mind-blowing. In just one sector, premium lump charcoal production, a single automated packaging line can process over 44 million pounds of product annually. That's tens of thousands of tons of finished fuel, requiring an unbroken supply chain of sourcing, packaging, and transportation. This intensity of operation demands perfect synchronization of every stage, from timber harvesting and days-long carbonization to the instant bagging of finished product that ships worldwide. Charcoal, born from living wood and forged in the fire of sealed kilns, is the result of a remarkable marriage between natural abundance and human engineering. It's a process where wood sacrifices its physical mass and moisture to preserve what matters most in its remains: pure, stable energy, locked away in the form of carbon. Every single charcoal block becomes proof of how humans learned to tame the element of fire, transforming forest resources into a compact and incredibly efficient energy carrier that continues to drive global civilization forward, despite changing eras. When we look at the charcoal production map, it becomes clear that the world is sharply divided between giant producers and equally massive consumers. Today, the undisputed leader in global exports is Indonesia. Just imagine, this country supplies nearly 22% of the entire global charcoal market. Its annual revenue from selling this product exceeds $400 million. As for those buying this resource, that's where things get even more interesting. China leads the world as the top importer, accounting for over 11% of global imports. This isn't just about culinary traditions. Charcoal is irreplaceable in high-tech manufacturing. Think pure silicon for semiconductors. Right behind China, Saudi Arabia, Japan, South Korea, and the US. In these countries, demand comes from two places: the restaurant industry and backyard culture, which pumps billions into the economy every year. The total value of global imports in 2024 alone, nearly $2 billion. Technology keeps pushing forward, especially when it comes to efficiency. Modern plants using pyrolysis retorts, those same ovens we talked about, can squeeze every last bit out of the wood. Traditional earth pits. They give you 15 to 20% charcoal from the wood you load in. That's it. But modern systems, they're pushing 30, even 40% yields. That's massive for the environment. Same amount of fuel, millions of acres of forest saved. And here's the thing, agricultural waste is the new game. Coconut shells, corn cobs, making charcoal without cutting down a single tree. These numbers prove something crucial. Charcoal isn't some relic of the past. It's a dynamic market adapting to modern demands. We're talking billion-dollar operations, cutting-edge material science, and a lifeline for billions of people worldwide. Every ton of charcoal crossing the oceans, it's a piece of a massive energy puzzle. And production efficiency isn't just a nice-to-have anymore. It's the key to keeping our planet in balance. Every year, the world generates hundreds of millions of worn-out car tires. That makes them one of the largest and most problematic types of solid waste our modern civilization produces. When tires reach the end of their usable life, they barely decompose naturally. Why? Because they're made from complex mixtures of synthetic and natural rubber, carbon black, polymers, and steel cord. At landfills, they take up massive volumes. They accumulate for years, and they create serious environmental risks, including fire hazards, toxic chemical release, and contamination of soil and water. At the very beginning of this technological chain sits a massive stream of used automobile tires, continuously forming across the entire world. Every single day, tires come off passenger cars, trucks, buses, construction equipment, and agricultural machinery, all worn out from tread wear, microcracks, deformations, or rubber aging. They're no longer safe for the road. But from an engineering standpoint, they're still a complex multi-component material packed with valuable raw materials. Inside every tire, you've got layers of rubber loaded with carbon black, polymer additives, textile fibers, and steel cord that gives the whole structure its strength. It's exactly this combination that makes tires difficult to dispose of, but at the same time, incredibly valuable to recycle. Collecting these tires happens at multiple levels. They accumulate at tire shops, auto fleets, service stations, logistics centers, and specialized waste collection points. From there, they're hauled by truckload to large processing plants. When entering the facility, vehicles go through weighing to record the raw material mass. Then the tires get unloaded onto open or semi-enclosed temporary storage areas. Here they can pile up in massive stacks. Think black hills of rubber, designed for continuous feed into the processing line. Before the tires actually hit the processing stage, they undergo initial inspection and prep. Workers or automated systems check their condition, paying close attention to contamination levels. Some tires might be covered with a layer of dirt, grease, asphalt residue, or debris accumulated during use or storage. These contaminants are undesirable because they can damage equipment or degrade the quality of the final rubber crumb. That's why excessively dirty tires get rejected or sent for preliminary cleaning. Special attention goes to foreign objects that sometimes remain inside the tires. Cavities can contain rocks, metal chunks, wood, or even fasteners that accidentally got in there during operation. Before feeding into the shredding units, these objects are removed manually or with specialized mechanisms. This is a critical stage because foreign solid inclusions can cause emergency line shutdowns or accelerated wear of blades and cutting elements. This preparatory stage produces a relatively uniform stream of raw material, ready for mechanical processing. Tires that pass inspection move to the initial shredders already free of excess contaminants, allowing the plant to operate stably and continuously. It's at this exact moment that used tires definitively stop being a problematic waste product and transform into a controlled technological resource, from which materials for modern road infrastructure are subsequently manufactured. After this, the tires enter the primary shredding zone. Here, massive industrial shredders with slow rotating shafts and cutting teeth do the work. Each tire is grabbed by the mechanism and literally torn into large fragments several inches in size. The process involves significant mechanical stress and noise, so equipment is housed in enclosed units with dust collection systems. Even at this stage, some of the steel cord begins separating from the rubber, but the main separation happens later. Shredded fragments are conveyed by belt systems to the next crushing units. Here the material goes through several size reduction stages, gradually transforming into rubber crumb. Magnetic separators work simultaneously, extracting steel cord and wire. Magnets are positioned above conveyors or built into drums, and they continuously separate metal, which drops into separate containers for further processing as scrap. Textile fibers used in some tire types are separated using airstreams and vibrating screens. At the output of this section of the line, cleaned rubber crumb of various fractions is formed. It's additionally screened to achieve a stable particle size distribution. For rubber-modified asphalt production, controlled particle size is critical because it determines exactly how the rubber will interact with the bitumen. Oversized particles distribute poorly in the mix, while particles that are too fine can behave almost like filler and alter the bitumen's viscosity more than needed. Before blending with bitumen, the crumb is typically dried and heated. Even a small amount of moisture can negatively impact the quality of the final mix, so the material is passed through drying drums or chambers with controlled temperature. Heating also makes the rubber more elastic and prepared for contact with hot bitumen. At this stage, the plant is already handling material flows measured in tens of tons per hour. Meanwhile, in another part of the facility, they're preparing the bitumen. It's stored in large insulated tanks and kept heated so it stays liquid. When it's time to mix, the bitumen gets pumped into special reactor mixers or kettles, where they gradually add the rubber crumb. The temperature in these units is typically much higher than in regular asphalt production, because the rubber needs time and heat to start interacting with the bitumen. During mixing, the rubber crumb particles absorb the lighter fractions of bitumen and swell. This isn't just mechanical stirring, it's a physico-chemical interaction that transforms the binder's properties. The mixture becomes more viscous and elastic, handling temperature swings and traffic loads way better. Mixes run for a set amount of time to hit that uniformity sweet spot, and then the rubber bitumen blend is ready to roll or store temporarily. From there, this material either heads straight to asphalt concrete plants or gets hauled in special insulated tankers. At the plant, it becomes the binding base for producing asphalt concrete mix with crushed stone and mineral fillers. The finished rubber-modified asphalt is laid down pretty much the same way as regular asphalt, but it behaves differently once the road is actually in use. Roads with this surface dampen vibrations better, produce less noise from tire contact with the pavement, and maintain their integrity longer without cracking. The elasticity that rubber provides allows the surface to better handle temperature swings, especially important for regions with cold winters or scorching summers. This reduces the need for frequent repairs and extends the overall life cycle of the road. At the plant scale, this entire process looks like a continuous flow of materials, where waste gradually transforms into an engineered product. Millions of old tires that would otherwise sit in landfills or illegal dumps for years become part of road surfaces. This not only reduces environmental impact, but also allows for partial replacement of virgin materials, cutting down on resource consumption. That's why rubberized asphalt is increasingly viewed not as some exotic option, but as one of the practical directions for modern road construction. In the United States, the problem of disposing of worn-out car tires is massive too. Estimates show that roughly 300 million old tires are generated annually in the US, a huge waste stream that demands effective management and recycling. The good news? The situation has improved dramatically over the past few decades. Back in the 1990s, the US had over 1 billion old tires sitting in stockpiles. But thanks to government programs and a growing recycling market, that number has dropped by more than 90% to a significantly lower level in the 2020s. Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, this is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script, it's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear, it migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxin's inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methylmercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest, and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting: cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would stop, lights would go dark, and space engines would fall silent. And yet, it's so rare that the entire world fights over every single gram. But here's the real kicker. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that'll flip your understanding of the metal-holding civilization together. Tungsten is a true engineering phenomenon. Its unique properties let us push the boundaries of what's possible in technology, from deep underground to the heights of space. Its story, a story of endurance and unmatched strength. Tungsten is element 74 on the periodic table, one of the transition metals. It has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. To put that in perspective, that's a temperature where most other metals would have vaporized long ago. On top of that, tungsten has the highest tensile strength of any pure metal, at temperatures above 3,000 degrees Fahrenheit. It's incredibly hard and dense, making it irreplaceable for applications demanding maximum resistance to wear, deformation, and extreme temperatures. Tungsten doesn't occur in pure form. It's extracted from ores, with the most common being wolframite and scheelite. Wolframite is a complex compound of iron, manganese, and tungsten, while scheelite is calcium tungstate. These ores, hidden deep in the Earth's crust, are the raw material for all subsequent industrial processing. The world's major tungsten producers include countries like Vietnam, China, Russia, and Canada, which hold significant reserves of this strategic metal. The tungsten extraction process is a complex sequence of mining and metallurgical operations. It starts with exploration and ore extraction from underground mines or open-pit quarries. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep within the earth. It's tough, dangerous work that demands cutting-edge technology and strict safety standards. Thousands of tons of ore are hauled to the surface every single day. After extraction, the ore heads to a processing plant. Here it goes through several stages to separate valuable wolframite or scheelite from other rock. First, the ore gets crushed in crushers and mills until it's a fine powder. Then various enrichment methods kick in: gravity separation, magnetic separation, and flotation. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The concentrate is then processed at metallurgical plants to extract pure tungsten. It's a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent roasting to produce tungsten oxide. The tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. The result is a fine tungsten powder, which forms the foundation for all subsequent products. From this powder, through sintering, tungsten rods, bars, and other blanks are formed. Tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, creating a dense, strong material. One of the most critical applications: manufacturing tungsten carbide. Some seriously tough stuff. These alloys combine tungsten with carbon, plus cobalt or nickel as a binder, creating one of the hardest man-made materials on Earth. They're used to make cutting tools, drill bits, end mills, lathe inserts that can slice through the hardest metals and alloys. Without tungsten carbides, modern manufacturing, metalworking, and oil and gas extraction would grind to a halt. A single pound of tungsten can become a drill bit capable of boring through thousands of feet of rock. Talk about efficiency. Tungsten also sees heavy use in military applications for armor-piercing rounds and bullet cores. Thanks to its extreme density and hardness, tungsten alloys have exceptional penetration characteristics, delivering devastating effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is indispensable. It's used to make filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components that need high heat resistance and electrical conductivity. Because of its sky-high melting point, it's used in the aerospace industry for parts exposed to extreme temperatures. High-temperature tungsten alloys are used in jet engines, turbines, and other devices operating under extreme heat. Alloying with tungsten boosts the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with way less toxicity. On top of that, tungsten's used to make ballasts and counterweights in race cars, aircraft, and yachts thanks to its crazy high density. It's even a component in some jewelry because of how hard it is and how resistant to scratches. Tungsten is one of the rarest elements in Earth's crust, which makes mining and producing it especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential resources that haven't been explored yet, the total volume could be significantly higher. That's obviously way less than reserves of metals like iron or aluminum, which really highlights its strategic value. Global tungsten production each year, measured in tons of pure metal, or tungsten oxide equivalent, fluctuates, but in recent years, it's been somewhere between 85,000 and 100,000 metric tons annually. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine this. You could take a worn-out tool that's already served its purpose and transform it back into something brand new, without spending the energy and resources to mine ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is one of the most advanced and efficient processes among all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number. It shows just how valuable this metal is and how much economic sense it makes. Where does used tungsten come from? The main source of secondary raw material for tungsten is, of course, worn-out carbide tools. Those same cutting tools, drill bits, milling cutters made from tungsten carbide. After heavy use, they wear down, lose their edge, or break. Instead of tossing them in the trash, they're collected and sent to recycling plants. Other sources include scrap metal containing tungsten, leftover waste from tungsten product manufacturing, plus some electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of mining ore and initial processing. Recycling dramatically reduces the environmental footprint of tungsten production. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production more green and responsible. Can metal burn brighter than the sun? Sounds impossible, but one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, Large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1,650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder, with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Every year, over 1,000 giant ships are sent worldwide for scrapping, each weighing up to 50,000 tons and stretching nearly 3 football fields in length. It's like dismantling an entire floating city, with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster is inevitable. But here's the most amazing part. Inside each of these massive vessels hides something that turns scrapping into a real treasure hunt. Workers risk their lives among plasma cutters and toxic fumes to extract these valuables. What exactly are they looking for? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone keeps quiet about? Stay tuned. What you'll learn next will make you look at every ship in port with completely different eyes. Why is ship recycling so important? Vessels that we typically imagine as enormous floating megastructures can be nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for sea travel and cargo transportation. But beyond their massive dimensions, these ships have extremely complex internal structures. Hundreds of feet of cables, pipelines, shafts, and various safety and comfort systems, plus countless different elements and mechanisms that perform different functions. This entire architecture isn't just scrap metal, but a complex organism that must be very carefully and properly dismantled when the ship reaches the end of its service life. It's critically important to properly remove all hazardous substances from the vessel that may have accumulated during its operation. These can be bioactive substances, toxic paints, fuel residues, lubricants, chemicals that, if handled improperly, can contaminate the sea, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a natural disaster. However, scrapping these maritime giants also has a very bright positive side. The metal from which the ship is made is excellent and valuable raw material that can be recycled and returned to production. This metal is used for building houses, machines, construction structures, and also for creating new vessels. This way, it's possible to reduce the need for smelting new steel, save energy and resources, and also reduce the amount of waste. Metal recycling from ships becomes an important link in the closed loop of modern industrial economy. Scrapping such huge objects also makes it possible to free up ports where old ships are standing, so new, modern vessels can take their place. This allows optimizing the work of naval bases and promotes fleet renewal. Additionally, proper recycling helps reduce operational costs for maintaining old ships and improves environmental standards in the maritime industry overall. The ship is delivered to special ship graveyards. These are usually coastlines with shallow water or special slipways. These locations aren't chosen randomly. Shallow water coastlines allow easy approach of the ship to shore, where it can be safely moored and dismantling can begin. Often these are small bays or beaches where the giant vessel is specially brought, so it doesn't interfere with maritime traffic and doesn't damage port infrastructure. Slipways, in turn, are large platforms or special structures where the ship is placed for dismantling on land. They're equipped with everything necessary for convenient and safe work: crane equipment, metal cutting tools, waste removal systems. One of the main tasks for specialists is ensuring environmental safety. After all, during operation, the ship accumulated many substances that, if handled carelessly, can harm the environment. These can be not only lubricants and fuel residues, but also toxic paints or chemicals. Therefore, the entire dismantling process begins with removing all such substances. Fuels and lubricants are drained into special containers and taken away for recycling or disposal to avoid getting into water or soil. Similarly with electronics and furniture, everything that could potentially harm nature is removed as a priority. This stage requires speed and maximum caution so that environmental standards aren't violated. After the ship is cleared of all hazardous and household items, the direct dismantling of the hull begins. And this is the most complex and dangerous part. Using special plasma cutters and gas torches, large steel structures begin to be cut into small pieces. This involves both hand equipment and heavy machinery, cranes, lifts, special manipulators. Plasma cutting allows very precise, fast and efficient metal division that will later go for remelting. The dismantling process itself happens sequentially, stage by stage, starting with the most hard-to-reach or dangerous zones. Metal sheets, beams, decks, and internal partitions are carefully separated so as not to damage structures that might still be needed for analysis or recycling. The complexity is that giant elements are often unevenly distributed and may be under tension, and due to corrosion or hull deformation, some parts can unexpectedly drop or fall at any moment. It's also important to emphasize worker safety. During plasma cutting, hot sparks and toxic fumes arise, requiring special protection from workers, respirators, special clothing, and constant air monitoring. A small mistake or neglect of rules can lead to serious injuries and accidents. Therefore, at every step, the process is regulated by strict safety rules, and the entire site is covered by fire suppression systems and medical support. Dismantling the hull and main steel structures of the ship is, without doubt, an extremely important and complex stage of scrapping a giant vessel. However, after this large body of work is completed, the job doesn't end. Ahead lies another massive phase that requires no less attention and certain skill, as it concerns dismantling and sorting countless smaller, but no less valuable and complex materials. One of the most massive and complex processes is working with cables. The ship contains hundreds of miles of cable networks that provide power and communication between all systems. These are powerful steel cables with insulation made of plastic, rubber, and possibly using non-ferrous metals. Cables don't just remain at the recycling site, they're carefully removed, processed, and sorted. Separating the metal core from insulation materials makes it possible to send pure copper or aluminum for remelting, and the insulation layer for recycling as raw material for new polymers. Workers must act very carefully not to damage long cable pieces, and also observe safety techniques due to the presence of residual substances or rust. Another important category of materials is insulation materials that line or fill the ship's walls, technical rooms, and pipelines. Insulation is often made from special materials, mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After removing insulation, it's sorted and sent to specialized enterprises where these materials can be recycled or disposed of without harming nature. Working with ventilation systems also requires thoroughness. Ventilation pipes and units that were used for air conditioning and circulation in different parts of the ship are dismantled and cleaned of dust, lubricant residues, or other substances. Metal elements of systems typically undergo quality remelting, and plastics or rubber often become raw materials for new products. Special attention is paid to water supply systems and sanitary installations. On board the ship are complex shut-off mechanisms, pipelines, fittings, mixers, tanks, and other equipment. Pipe parts and equipment are carefully separated, cleaned of sediment, lubricants, and other contaminants to be sent for remelting or appropriate recycling. After all, these materials may contain toxic substances, so their disposal or recycling happens strictly according to regulations. No less important is dismantling equipment from the engine room. There are engines, generators, pump systems, turbines, and other complex machinery that typically has significant weight and contains large amounts of metals, including non-ferrous ones. Such equipment is mainly repaired and reused or dismantled into parts, some of which undergo recycling. In individual cases, engines even go for sale as used spare parts, avoiding becoming scrap metal. Furniture, household appliances, lighting, and other interior items of the ship also aren't just thrown away. They're removed and sorted. Wooden, metal, or plastic parts undergo separate recycling or disposal. In some cases, furniture, if it's in good condition, is sold for reuse, and all paints, varnishes, and certain polymer materials are taken for environmental recycling to reduce pollution.